everyone. I am Neela, and as Lauren just mentioned, me and Sushim are from the Systems Engineering Center of Excellence in Applied Materials. Today, we will talk about how we used Capella MBSE models to build and develop one of our key process components, and how we use the MBSE model to derive a failure mode analysis and FMECA out of it. This is the flow of the presentation. We'll start with a brief introduction to applied materials, what we do and what we are. And we'll start talking about how we used MBSE methodology to design electrostatic chuck. I'll talk a little more about that in the presentation. And from the MBSE model, we got a little greedy and wanted to do more. So we started exploring ways to build a FMECA analysis from it with the help of Python scripts. We'll talk about how we implemented it and what are the advantages over the traditional FMECA approach. And now, where we are now and what are the next steps for us. Applied Materials, we are the equipment makers for semiconductor and display systems. So we are the machines behind the chips which enable pretty much all the new age companies, AI, big data, smart automotives. Now, these mammoth machines, the typical product, what we call is a wafer, which eventually gets converted into chips. And these chips, there are a few nanometers of patterns, and the machines what make them, you can imagine the precision what is needed to build those. So if you look at a typical manufacturing tool, the picture what you have on your screen, most of the processes are under vacuum. We have robots moving wafers in and out of vacuum and into the process chambers where the wafers actually get made. There is toxic gases coming in either to deposit or to remove material from the wafers. A lot of processes need plasma for their processing, and so on and so forth. So this is truly a multi-physics and a multidisciplinary system. It's quite complex. It's a system of multiple systems. Now, we are in the early phases of adopting MBSE methodology into our product development cycle. We are looking at component development right now, and eventually we'll start building systems using MBSE. The advantages, to list out a few, what MBSE can offer is, just to begin with, the wafer performance. If you start looking at the system as a whole, of different physics and different groups involved, we can reduce the number of iterations back and forth, and the risk retirement process can be better. So, right away, there can be an improvement in the performance of the wafer and eventually performance of the chip what we make. As we just saw, it is a system of systems. How do we bring all the engineering teams together? Again, MBSE can act as a single source of truth for us to derive and modify information. Time to market is the key. Again, if we did bring down the overall number of iterations, we can shrink the overall product development cycles. And if we can build traceability to the requirements and to changing customer needs, we can stay ahead of the market inflections. We are yet to experience all the advantages of what MBSE can offer us, but we are starting to appreciate as we are building components using MBSE. Now let's talk a little more about the wafer performance and how what kind of control we would need on the process parameters and the components. To list down a few, how we will bring in the gases for wafers to form, how we will distribute plasma evenly over the wafer, or for that matter, heat. All of these eventually affect the performance of the wafer. And as the node size drops down, as the chips are getting smaller, our tolerance for these parameters really becomes tighter. A very simplified schematic on the bottom, let's say gases coming into the process chamber, and we have a means to distribute the gases evenly over the wafer, the process can be enabled by plasma. Now, wafer in most of these processes is supported by something we call chuck. Chucks can be of different types. Here, we chose an electrostatic chuck. Now, the purpose of the chuck is to hold the wafer in its place and support its transfer in and out of the process chamber. Now, we started using MBSE. MBSE models to design the chuck for a new application. To provide a few more details on what electrostatic chucks are, their primary purpose, as I just mentioned, is to hold the wafer during the process. They have to be planar. There shouldn't be any sliding because eventually these affect the wafer thickness uniformity. And one additional function can be to provide heat to the wafer or to cool the wafer down, and do it uniformly, so all the entire surface of the wafer sees the same temperature pretty much. So another complexity gets added where there may be a heating filament or a cooling loop in the electrostatic chuck. And more often, these chucks offer support to plasma processes. Either they couple with the plasma process directly, or they just have to see through the plasma process. So this is a very critical component, very close to the process, and directly impacts the performance of the wafer. On the right is a schematic. There are multiple types of chucks depending on how charge is coupled along with the wafer. There can be single polar, bipolar, but the physics is again multi-physics, offering different functionalities which the chuck has to support, and there can be different operating mechanisms depending on the process and the kind of wafer we are looking at, and the structure can get complex. There can be multiple layers depending on heating or cooling. So when we started using MBSE to develop an e-chuck for a very specific application, and Sushim will talk through the design and development part of it.
Thank you for that introduction, Neela. So, just like Neela explained to us, electrostatic chucks are a very critical component in our equipment and have a big impact on the performance of our machines, which then lead to, really the performance of the chips that we make through using these machines. So, when we started off our MBSE adoption journey and we're looking at, the right type of projects and products to utilize this methodology on, electrostatic chucks were a very good candidate for us for a few reasons. One is the scope in terms of the size of the electrostatic chucks was fairly manageable. They have anywhere between 15 to 30 different components based on the application requirements and the actual type or the mechanism of the electrostatic chuck. And then the other reason was, they are a critical component in our equipment. So we figured, hey, let's try and use that or use MBSE for the development of that kind of an assembly or a sub-assembly and see how that impacts our overall performance. So when we started off, or before we even started creating MBSE models for electrostatic chucks, we set a few primary goals, right? And these are the goals listed on the top left corner. We said we want to have or demonstrate traceability from process requirements to all the way to the design, right? Part numbers in the design. And this is something that we lack today without model-based systems engineering processes and tools in place. So we often run into scenarios where we have requirements documents, we have a design, we have some kind of analytical models as part of the design, but there is no traceability or link between them, and it's hard to go back and try and find out exactly which requirements document or which requirements document version was applicable to a certain design. So we wanted to try and close that gap. The second was creating a library of standardized e-chucks. So electrostatic chucks, like I mentioned, are commonly used in our equipment, but there are a large variety of electrostatic chucks, right? It depends on the exact process application on the tool. It depends on the heating requirements, cooling requirements, size of the wafer. So there are quite a few parameters that impact the design of an e-chuck, and we have a whole variety of them available. And we wanted to use MBSE to help create a standardized library of e-chucks, really to enable and encourage more reuse and commonality between our equipment. Uh, and then the third idea here, or the third goal, really was knowledge capture for future iterations, right? Knowledge capture to share that knowledge capture for collaborations. But really, when we say knowledge capture for future iterations, what we mean is we often do projects where we are making some kind of evolutionary improvements on a design, right? Not necessarily a ground up design. And whenever we want to have those changes or upgrades on an existing design, I'm sure you can all understand, right, that it's important to first understand how the existing design works. And as we are growing as an industry and as an organization, sometimes it's hard to go back and find all the documents or the people who were involved in that first version, right, or the existing version of the design. And that's another goal we wanted to achieve using model-based systems engineering, was capture the knowledge, capture the design intent, the requirements, the validation data, so that when in the future there is another team looking at making an improvement to the design, they have a good starting point. So what we see here is a physical architecture diagram in Capella. It's a fairly simplified version. I'm showing just a few components in the electrostatic chuck. And let's start by taking a look at the physical components, right? So in the bottom right corner, we see the yellow boxes, which are the physical components. The biggest one is the ESC, or the electrostatic chuck. And then the first component in that is called the puck. This is really the part of the ESC that the wafer rests on. And at the bottom is the cooling plate, which helps with heat transfer for cooling the wafer. And then these two components are connected using a bonding adhesive. Again, right, I'm showing about 3-4 components here. The actual assemblies have anywhere from 15 to 30 different components. After, or along with the definition of the actual physical components and the structure of the components, we also define the critical functions and behaviors associated with each component. So in the puck, for example, we have a puck behavior with two functions. One is support wafer, and then the other one is called transfer heat. And we're using transfer heat as an example for this particular demonstration. So you can see I've defined a transfer heat function really for all the components here. So along with the puck, we have the bonding adhesive with a couple of functions defined. Then we have a cooling plate with its function defined. And then along with the physical components, right, our system of interest here is the ESC, but we didn't want to limit our model just to the ESC, right? Within the ESC, or the electrostatic chuck, the model itself gets fairly complicated, but that isn't enough to achieve this goal of knowledge capture, right? For knowledge capture, really what we want to do is also model in some of the system level actors, right? Or system actors, or really the stakeholders on our equipment that interact with the ESC and have a significant impact on the design and the performance of the ESC. So in this case, if we see above the ESC, we have defined a system actor called a gas, and then there is a system actor called the wafer. So this is the silicon wafer that Neela showed you in her slides. They're typically these days 300 millimeters in size, but we still have some 200 millimeter equipment. But finally, our tool and our ESC, they're all designed to impact the performance on the wafer, right? We manipulate the wafer using different multi-physics processes to really create chips on the wafer. So as you can understand, the wafer is a very important element in this overall system of stakeholders. So we've modeled in the wafer and defined certain functions for the wafer. And then we've also, on the left side, as you can see, a few other system actors and functions. We did create those objects and define those objects in the physical architecture, so that we could define exactly how those interact with the electrostatic chuck as well. So along with the physical components, system actors, and functions, the two other things that we have modeled here are functional exchanges and physical links, right? So the functional exchanges here, using which we've created this blue functional chain, we've called that functional chain heat transfer, as you can see. These are the functional exchanges really to show the heat transfer mechanism all the way from the wafer to the source of your cooling fluid, right? We are showing a cooling heat transfer mechanism here. So we've shown those functional exchanges. And then we've shown also the, in red, as you can see, the physical links, right? Or these are the different types of physical interfaces that we see on the system. Some of the obvious ones, right, within a system, we've shown the physical interfaces between the puck and the bonding adhesive and the cooling plate. But again, just to capture this big picture goal of knowledge capture, we've also shown the physical interfaces with the other stakeholders on the system. And this is where our the upcoming discussion plays a big part. So for example, we've shown in the bottom you can see the cooling plate has physical interfaces with a supply hose and a return hose for the cooling fluid, and then the puck has physical interfaces with the wafer, the gas, process chemistry, and plasma, right? These are other parts of the environment that the electrostatic chuck operates in, and we've modeled those in as well. In some cases, right, we have physical links or interfaces that are electrical. In some cases, right, they're purely mechanical in terms of maybe a threaded interface. Um, but we also wanted to use that particular feature in Capella to show other system level interactions, which are maybe just in the form of a contact, right, or an exposure. So we have a few over here, as you can see, where we are just calling them physical contact. And all that means is, hey, the puck comes into contact with a gas and the wafer, or chemistry and plasma. So as we defined, started building this model and adding all this level of data really into the model, we challenged ourselves to make more out of this model, right? Of course, these three goals that we've listed are important, and as fellow systems engineers on the call, I'm sure I don't have to convince anyone of the benefit of these three goals. But since we are still in an adoption phase, Neela and I and others on our team, as part of this MBSE adoption team, we often get challenged on, more tangible and more short-term outputs or benefits of MBSE, right? We are often asked, hey, well, how is this helping me in my job today, right? How is this helping me get my design released and design released correctly? So we do challenge ourselves on finding more and more applications for this, as we are also still learning more about MBSE. And one of the items that really stuck out to us as we built this model was, hey, this model is, we're adding a lot of data in here that could be very useful for risk analysis. So currently at Applied Materials, like in many industries, we use FMECAs for our risk analysis, right? We do build reliability models, usually in the form of block diagrams and stuff to help with that FMECA. But really, our risk analysis is in the form of a FMECA matrix, and we'll get into a little bit more about what that process looks like today. So before we get into the details, let's do a quick recap of what a FMECA really is, right? So FMECA stands for Failure Modes, Effects, and Criticality Analysis. Some of you may know it as an FMEA. Although the terms are really used interchangeably these days, there is a difference between the two. The definition really for FMECA is it's a systematic and structured approach used to identify and prioritize potential failure modes of a system, process, or product, assess their effects on system performance or safety, and determine their criticality based on severity, occurrence, and detection. And this right determination of the criticality based on severity, occurrence, and detection is what makes a FMECA quantitative, because we do use numbers and rankings to generate a score. And that is where it really differs from FMEAs, which they started off as, which were more qualitative than quantitative. Anyways, moving forward, we use the term FMECA and FMECA, but really you could apply this to FMEAs as well if that is what you are using in your industry. In terms of the history of FMECAs, they started off as FMEAs, first developed and used by the US military in the 1940s, and were later, adopted by NASA in the 1960s for the Apollo missions. And that really, made them more popular. And today, FMECAs, the use of FMECAs has expanded to to pretty much every other industry, right? Including semiconductors that Neela and I are a part of, energy, aviation, automotive, electronics, railways, medical devices, pharmaceuticals, and then even some of the non-hardware type of industries, if you will, right, where which include banking and financial services. We use FMECAs on business processes and of course software development as well. So the use of FMECAs has definitely expanded and is an integral part of product development these days. There are many different types of FMECAs based on your product, project, and industry, but some of the common types include software FMECAs, process FMECAs, functional hardware system, as well as safety FMECAs. For our purposes, using the electrostatic chuck as an example, we are going to really be looking at a hardware FMECA. Okay, so as I was mentioning, right, FMECAs are now used you know widely across multiple industries, and what that has done is also each of these industries have their own standards, and each of the standards now has their own guidelines on the process of creating a FMECA. But looking through all of them, they all have the same philosophy or the same essence, really, that can be boiled down to this type of a flowchart that we see on the left side. So essentially, you create a project team and you start off the process with a team. You define the scope of your FMECA, really, which is like defining the scope of the system. What is your system of interest that you are doing your risk analysis on? And then for a hardware FMECA, which we are using as an example, you start off by defining a parts list. Because right, when we design hardware, we are all used to dealing with parts and a list of parts or a BOM of parts, and we start off with that list of parts. After you have a list of parts, you define the functions for each part, right? Because those are very important for then figuring out or determining the potential failure modes. And it is this process of defining the function today, when you do it as a team, you really rely on right, the brainstorming of that team, and really the brain power and the expertise that is available in your project team and that particular meeting, because those aren't always defined very well, and we'll get to that in the upcoming slides as well. Once you have the functions defined, you brainstorm potential failure modes, you talk about the effects of the failure modes, list out any controls or detectability that you may have. Then you start giving rankings, right? You estimate a ranking or a rating for the severity of the failure, the occurrence or the probability of the occurrence of the failure, and then you give it or you calculate really the criticality score, right? And then once you have a score based on the guidelines for your project or your organization, if that score is below a certain threshold, you call it good, say, okay, hey, it's a low risk, we'll continue down the current design path, and we move on to the next line item. Or if it is above a certain threshold, then you say, okay, well, this is not acceptable. Let's now brainstorm some design improvements, or perhaps we already have some design other options in mind. Let's see how basically a design alternative could impact this particular score. So we repeat this process on the design alternative, and when we find an alternative which has a score below the threshold, essentially that becomes the design alternative of choice, and that is what we design the system to. Once we go through all the parts and the functions, right, if there are no more actions to take, we call this good and we move on. So what are some of the shortcomings, right, or challenges with the current process? Now, I'm sure as systems engineers who've done this for many years, we can perhaps identify areas of improvement at every step if we wanted to. But for today's demonstration, we really wanted to focus on the first few steps. And I'm sure it's fairly obvious to say that in this type of a serial process, if you don't do the first few steps very well, it is going to have an impact on the rest of the steps as well, right? So if you don't define the scope of your system, don't define all the different functions and the potential failure modes well enough, your overall quality of your FMECA or your risk analysis is going to be low. You won't identify all the failure modes, so you're not going to identify all the areas where you need to have mitigation or perhaps design improvements. And this is going to lead to right cost and time overruns and safety and other liability risks as well. So if we look at really right, the challenges that we personally see in our industry, and many other high tech industries that we've been a part of before. If you look at the items of defining the scope, defining the parts list, fairly easy to achieve, right? You can export a bomb from an existing, or from your current CAD design perhaps, and you have a list of parts. But when we get into those items of defining the functions for each part, is where things would get a little more vague, if you will, right? Because without an MBSE model today, perhaps we have good, right, even if we have good requirements documentation, say we've done a thorough job of documenting all the way from marketing, to functional, to hardware and design requirements. Those design requirement documents themselves don't always have this type of information that assign functions at the part level, right? Even if we have a functional requirement document at a system or at the assembly, that document itself doesn't necessarily have the allocation to show that, okay, this function needs to be performed by this particular part. It just talks about the overall functions of a system. In this case, it would be cooling the wafer, heating the wafer, chucking the wafer, not necessarily, right, broken down at the component level, because that component architecture hasn't been defined at the functional requirement level, right? So what we end up having to do is we spend a lot of time early on in these meetings with 5-10 people from the project team. We spend time essentially trying to come up with a good list of functions that each component is performing, right? And the quality of that output really depends on the people that are available in that particular meeting, right? How long, at times, right? How long have they been part of this particular project, or the project team, or the organization, the type of experience and the expertise that they have. So there are a lot of soft factors, if you will, that we have to depend on without giving the team good tools to come up with some of this information, right? At best, we may have a 3D model, we have some electrical schematics, maybe some gas flow schematics, but they're all discrete siloed documents, if you will. So we don't really enable the team to do this or do these particular steps very well. And this is where we think MBSE models can really help us out, right? So if we look at now, if you look at that same flow chart along with an MBSE model of the electrostatic chuck, let's see how the MBSE model can help with some of those steps. So the first step really is defining the scope of the system. Again, as part of our MBSE model creation, right? In the physical architecture, we do define that scope, right? Or we do define that system. In this particular case, our system of interest is the electrostatic chuck, and we can see that here in as physical components. But this also does show us what the other important system actors or stakeholders are on the system that do interact, right, with our system of interest. And if we wanted, we could choose to include one or more of those in our risk analysis as well. The second item on the flow chart is defining a parts list. Once again, since we have a physical architecture, we have that parts list. So here we can see in the ESC there are parts called the puck, bonding adhesive, cooling plate, and then within the puck there is another part. Typically we have anywhere from 15 to 30 parts, and that list is now directly available from your MBSE model, right? Makes things a little easier. Then the third item is defining the functions of each part, right? And this is where, as I was talking about today, it's an inefficient process where we spend the first few meetings as a project team just trying to define each of those functions and assign those functions at the part level. And now, really, if we have followed this Arcadia methodology, right, we've done the operational analysis where we define the operational capabilities and operational activities. We then go to a system analysis where we define the system functions, and then we break down those system functions and start allocating them to logical systems and then your actual physical system. If we follow that process and use the tool and feature, the Arcadia methodology and the tools and features of Capella, we've now already completed that, right? We've followed that to help us now define and allocate functions at the component level. Like, for example, here again, we are saying that, hey, it is the puck that is supporting the wafer, and then it is the puck, the bonding adhesive, and the cooling plate that all have to have a heat transfer function to effectively cool the wafer. So now we have a good, a well-defined list of functions for each component that is already available in the MBSE model. And now we get to something that isn't available, or that is again has a different level of challenge in terms of brainstorming at a component level, right? And these are the system level interactions. Today, if we look at a hardware FMECA or a design FMECA where we look at the system at a component level and functions at a component level, we often miss out on the system level interactions and the system level interfaces. And I'm sure many of you have experienced this before. When we see failures, right, whether they are reliability issues, safety issues, when we do start seeing failures on our products in use, they are often at these system interfaces, or at the system interaction type of a level more than the component level, right? We are all good at anticipating what could go wrong at a component level, but it is the system level interactions that often come back and bite us. And the quality of how well we can define those today with the current process, again, goes back to really the ability of the team to kind of come up with those, on the fly or through a brainstorming session in the meeting. But because we have this tool called Capella and all its features of defining these different system actors and functions and components, it gives us the ability to define these functional exchanges and physical links, which are extremely important as part of your overall risk assessment at the system level. Now, a couple of examples that we experienced, right, like real benefits of using it this way, in terms of the risk analysis. Let's take a look at this functional exchange that I have, between the puck and the wafer. So if you look at, towards the right hand top corner, there is a conduction functional exchange between the wafer and the puck. So over here, okay, today when we look at it just at the component level, we look at, hey, what could go wrong in the puck? But now when we look at this particular functional exchange, we now also think about, oh, what could go wrong between on this conduction path between our system and something that is outside our system. And that is a real risk. We've identified risks associated with conductivity or electrical conductance issues on the wafer itself that could impact our system. So we've experienced real benefits of looking at these system level interactions as part of our risk analysis process. And I'm going to hand it back to Neela to show you guys how we really use the MBSE model to now generate the FMECA matrix. Neela?
Yeah. So we have the matrix, and we wanted to get the data and organize it in such a way that we can make a FMECA matrix out of it. And Python interface seemed to be an easier solution to do that. So the starting point is building the right model with the components and all the interactions and exchanges. And we once we have the model, we can choose to build one FMECA from the physical architecture, or multiple FMECAs from different diagrams, logical or system, to see if a combination of subsystems makes sense. Or if you want to go deep into one particular component, that's where you come to a physical architecture blank. And the scope of the system in this case, we have restricted it to the e-chuck and its interaction with wafer, but we can start to look at the entire functional chain as a whole, the end, to identify if a functional chain breaks down, for instance conduction and the heat transfer, how would it impact the system and what would be the essential failure mode. Or we can just start to look at a component like the puck, if you see on the table on the right. We can do that. So the Python script offers us enough flexibility to either look at a component FMECA or a complete functional chain of FMECA. On the template, we went back and forth on identifying what may be the right approach. So depending on the kind of FMECA and depending on the type of team involved, we have multiple templates, and we essentially reported out the components, all the exchanges, and the physical links. Most of the libraries which are available on Python for Capella is used to extract this information in what we want, and the organization of data into the Excel. What we want is we've used mostly OpenPy Excel libraries. So the same template, as I said, can be looked at different ways: functional chains, the physical components, and we can identify the critical risks or non-critical risks when we compare it against the process. Now, what are the advantages against the traditional systems? What we saw while we are building this method is, if we have the right model to begin with, the list of failure modes can be quite comprehensive, including all the interactions, all the component level functions, and you can have multiple views of failure modes. This definitely is an increased efficient process, because we remove the time where engineers have to sit for a few hours from different teams and populate this Excel sheet. We can do it in a few minutes using the Python template what we have, and they can focus on the risk mitigation part of it. As we started using MBSE for failure mode analysis, one hidden advantage was capturing multiple failure modes which didn't come up while we were looking at FMECA using our traditional processes, particularly near these component level interactions. So this actually became a database for us, and we've documented it, which now we can extend it to other chucks, e-chuck or vacuum chuck. And definitely Python libraries made it more efficient, and we have multiple templates which we can use it beyond the same component, or beyond even the system. They can be used on any MBSE model with very little change. And even if someone is new to Python, the existing libraries make it easier for us to change or edit the scripts. Now that we got here, what are a few next steps for us? The first one is, can we, because the functional chains already have the failure mode information, can we populate the effects of failure mode directly from the MBSE model? So if we can fill in the other columns of criticality and severity ratings. Severity ratings, we already know them from the hardware. If we add them into the description tab while we are building the Capella model, and eventually through the scripts, if we can document those severity ratings, they also can be auto populated. Now, different teams look at different kinds of FMECAs. For process engineers, some we may be interested more on the process side. For safety engineers, they may be more interested on something like a leak detector. So all these different views can be made possible just with minor edits, and that's the next goal. How do we make the template standardized so any engineer or any team can make use of it and derive a FMECA of their interest? And at an organization level, we are trying to automate processes and make them more efficient. So from the data what we have collected in the field, such as the failure rate data, or the part numbers, and the validation and verification data we have either from the module testing or the system level testing, can we somehow connect this database to the MBSE model to read that data in a format where it can help build the FMECA model? So, for instance, we know if, let's say, two chucks out of 100 chucks fail in the field every year, is there a way to identify the root cause for those chucks and feed it into the MBSE model so we know the higher or the critical risks and rate them better? So, sorry, yeah. Yeah, so that's how we went from building of an MBSE model to building of a MECA matrix and failure mode analysis using MBSE and Capella. Thank you for your attention. You can talk to us, you can reach out to us on these email IDs.
Very good. We'll go for the questions and answers. First question, is there any plan to share the Python scripts that you've been developing for the FMECA export?
Yeah, some of them, which are generic enough, we can share them.
Okay, perfect. Thank you very much. And then second question that we have for now is, do you have any internal figures regarding basically what Capella helped you improve regarding productivity or quality improvements or anything else? Do you measure anything?
Yes, so we haven't done it on enough projects to, get conclusive data of sorts, but I definitely have some, early observations that we have seen on the projects where we did use this methodology. So we were, when we went into this thinking, hey, it's going to be more comprehensive and more efficient, we were expecting to get a benefit of time, right, or improved productivity from the efficiency. What really ended up happening was we didn't necessarily reduce the overall time we spent on risk analysis, but we started spending that time on better risk analysis. Because what we observed was, compared to our traditional FMECA method, this method was giving us twice as many, or in some cases, three times as many potential failure modes, right? Because now we weren't just looking at it at a component level, uh, excuse me, because we had a well-defined list of system level interactions and functional exchanges. We had a more comprehensive list that we could now spend, quality time analyzing. So yes, definitely higher quality with many more potential failure modes, and improved productivity, really, because we are now spending time on the right type of a discussion instead of trying to come up, with potential failure modes.
Okay, that's really great feedback. Thank you. Next question, let's go. How do you ensure the physical components enlisted in Capella are up to date with the ones on your CAD system?
Great question. So really, right, if we think about this asks us about, hey, do you have bidirectional traceability, right? Yes, we are generating FMECA from your model, but how do you then go back to make sure, perhaps, right, that yes, now your FMECA is still up to date, or perhaps the results from your FMECA are being fed back to your model and your CAD parts. So we don't quite have that bidirectional capability built in yet. Like we said, we are fairly early in our adoption journey, and just doing this one way export, if you will, from Capella to the FMECA using our MBSE model as a single source of truth, is that itself is a significant step up and an improvement for us. We do have some ideas on using a similar method to do Python based imports from your FMECA model back into your MBSE model, to share back the results. The other thing we can do is, we are building traceability from MBSE to our BOM structure. So we actually have part numbers and revision information that is being fed to the MBSE model. And if we wanted to make sure that the FMECA really is up to date, that is a piece of information we could kind of capture in the FMECA, right? Along with the part description, we could have a part number and the rev number, and then perhaps on a weekly basis or whatever, right, based on your project frequency, we run a check to see if your FMECA is still up to date with the latest Python export from your MBSE model, and try and match up those part numbers and rev numbers.
Okay, thank you very much. That's also a pretty thorough answer. Next question is, how do you evaluate the effects on your system of every failure of the FMECA?
So today, I think Neela touched on it a little bit, right? The use of functional chains in Capella is something we are trying to leverage more and more, right? So when we know that, hey, a certain function or a functional exchange fails, the functional chain gives us a very quick, visual feedback on seeing, okay, hey, if this particular transfer heat function fails, it is part of this bigger functional chain of heating the wafer, which means the effect of this failure is going to be that you're not going to heat the wafer well enough. So that's how we are using our MBSE model to analyze the effects.
Once again, thank you very much. Can you just tell us how many people in your teams are concerned by the use of Capella and these FMECA export scripts?
So we've So our core team of MBSE modelers really is limited to around 3 or 4 active modelers, and we've done this on about 2 different project teams. So if we look at really the people who've benefited of seeing this process, it's in the order of 10 to 15 engineers.